Hello, this is Miss Moore, and today during chemistry we'll be discussing stoichiometry. Today's essential question: how is stoichiometry used to predict the amount of reactant needed or product made? For today's lecture, you should have handy your periodic tables and your calculators. Okay, let's start with a quick overview, hopefully a review of chemical reactions. So, a chemical reaction involves changing substances. So, during a chemical reaction, one or more substances change into one or more new substances. So, the reactants are the things you start out with. And the products are the things that you end up with. Or it's the thing that you make, thing or things that you make. Okay, so in a chemical reactions, you start out with reactants, and these things change into your products, which are different than your reactants. And then we have to talk about equations. So an equation describes a system that rearranges atoms and bonds to make up new substances. So a chemical reaction is a thing that happens. Okay, you start out with one thing, you start out with your reactants, and you end up with something else. It's what you've actually done. An equation is what you write down on a piece of paper describing what actually happens. So that's kind of a quick review of reactions. So now let's talk about stoichiometry. So stoichiometry is a method of chemistry that uses a balanced equation to predict the exact amount of a product produced from a certain amount of reactants, or the exact amount of reactants needed to produce a certain amount of product. Okay, so again, stoichiometry is used as a prediction, okay, and we can use it to predict the amount of reactants needed or the amount of product produced. All right, so we need to learn some new conversion factors. And when we talk about conversion factors, remember we're talking about equalities. It's a way to change from one unit to another, or we're going to find out from one molecule to another. So an example of an equality is like 1 foot equals 12 inches. The units are different, but those two equal each other. So that's what we mean by equalities or conversion factors. All right, so the first equality is mole-mole ratio. And in this equality, we have mole known equals mole unknown. So our known and our unknown, what we're talking about is the molecules, I guess the atoms, or molecules that we're discussing. Okay, so the known is the one you know something about. It'll have a number attached to it. And the unknown is what we're trying to figure out. Really important when you're using the mole-mole ratio, you are not changing. And by the way, instead of writing changing you can write a delta, that means change. So you're not changing units. What you're actually changing or converting to is different to a different atom or molecule. Okay, So again, when you're using the mole ratio, you're not changing units. You're not going from, for example, feet to inches. You're going from, example, hydrogen to water. And it'll make more sense in a few minutes. So what you are doing is you are changing to a different atom or molecule. All right, the next conversion factor is mole known to molar mass known equals molar mass known. We used this before when we were doing mole conversions. The only difference is now you got to keep in mind that when we're talking here, known, known. Okay, this needs to be the same atom or molecule. And I forgot a C there, sorry. It needs to be the same atom or molecule. So we're going from mole of, for example, hydrogen. We want to get the molar mass of hydrogen, which we get off, remember, molar mass, that's from the periodic table. And then the last conversion factor is actually very much like the second one. 1 mole of unknown equals the molar mass of the unknown. So once again, in this case, we're going to have 1 mole of the same compound equals the molar mass of the same compound. So again, same atom or molecule. But the unknown is a different atom or molecule than the known. Okay, so let me erase all this stuff. One more time, I just want to make sure you're very clear about this. When we're using mole ratio, we are keeping the same unit. And the unit is moles. What we're changing or crossing out, if you would like, is the atom or molecule. Okay. For these two, we are changing units. We're going from mass to moles, or from moles to mass. What's staying the same is we're keeping the atom or molecule, keeping the same atom or molecule. Okay, so you can only change one thing at a time, either the unit or the atom or molecule. All right, onward. Let's talk about this mole ratio, and that's this pink one right here. So when I say mole ratio, where does that come from? Comes from the balanced equation, and so how does it work? So coefficients in an equation show the number of moles of each molecule or element being used or created in a reaction. So a coefficient, let's see, a coefficient, we're talking about these numbers in front of each atom or molecule. And there's actually an invisible coefficient there. There's one of those. Okay. And each of these coefficients we can look at as moles. Okay, so you could say that for every 1 mole of glucose, C6H12O6, and 1 mole of oxygen, when we mix those two together, or not 1 mole, sorry, 6 moles of oxygen. So for every 1 mole of glucose and 6 moles of oxygen that we mix together, we know we're mixing them together because there's a plus sign there, we produce or make 6 moles of carbon dioxide and 6 moles of water. Okay, so those coefficients have an invisible unit, and the invisible unit is a mole. So mole ratios can be used like conversion factors to compare amounts of substances. So what you do is that to make you make your own equality for each and every problem, and you set the coefficients in moles for the 2 atoms or molecules in the questions equal to each other. So for example, we won't do this problem, but just to give you an idea, if we had a question like how many moles of O2 are needed to make 18 moles of water. When we go to look at to make our equality, we see that the 2 molecules that we're interested in are O2 and H2O, right? And we look at our problem and we see we have 6 moles of O2 and 6 moles of H2O, which means our equality would be 6 mole O2, oops, let's not do that, 6 mole O2 equals 6 mole H2O. Okay, and then this is the equality that we would put in our grid. Okay, let's try a practice problem. So our practice problem, our example is how many moles of CO2 or carbon dioxide would be created from 3 mole of C6H12O2 or glucose. So first thing we'll do is we'll write this as a math problem. So we know we have 3 mole of glucose. And what we're looking for is how many moles of CO2. Okay, so we'll write our grid and we'll put our known in the grid, which is this guy right here. This is our known. We know something about that. So we'll have 3 mole C6H12O6 over 1. And now we need to find an equality to put into that area there. So let's see. We are at moles C6H12O6, right? And we want to get to moles CO2. So let's go back and look at our equality list and see if we have anything that has moles of C6H12O6, which by the way is our known, 2 moles of CO2, which is our unknown. So let's check our equality list. And it looks like we have this guy here, mole-mole ratio, right? Going from mole known to mole unknown. And just in case you forgot, when we're using the mole-mole ratio, that comes from the balanced equation. All right, so again, let's use the mole-mole ratio from our balanced equation. All right, so The two atoms or molecules we're interested in are C6H12O6 and CO2. So we have to put one of those on the top, one of those on the bottom. And since we have C6H12O6 at the top here, we need to put that on the bottom. So we're going to have 1 mole. Remember, the unit's the invisible mole, and also being that there's nothing there, we write a 1 there. So we have 1 mole C6H12O6 on the bottom. And on the top, we'll use 6 mole CO2. All right, let's cross out our units and check where we're at. So it looks like our mole C6H12O6 indeed crosses out our mole C6H12O6. And you'll note there that what we changed is not units, but atom or molecule. We kept the same unit. And we're left at mole CO2, which is what we were looking for. So we are now done with the problem, except for multiplying across the top, multiplying across the bottom, and dividing. So let's put 3 times 6 into our calculators, and that will give us, if I did this correctly, 18 mole CO2. And when we multiply across the bottom, 1 times 1 is 1. And when we divide, we end up with 18 mole CO2. And the very last step is sig figs, as is always the case. We do not use these moles here from the balanced equation as part of our sig fig, so we're just going to use our given, which is 3, which is 1 sig fig, right? So we have 2 sig figs there, so we're really just going to keep the 1. The 8's going to bump the 1 up to a 2. And 2 is not a good rounding of 18. Remember, whenever we drop a digit before a decimal, we need to put a placeholder, so we'll say 20 moles CO2. All right, so there's one of our practice problems. All right, let's try another one. So this time, what mass of glucose, or C6H12O6, would be needed to form 12 mole of H2O? So if we start by writing our problem as our question as a math problem, we will have, what do we know about? We know we have 12 mole. That's not going to work. We have 12 moles of H2O, and we want to know what that is. We want the grams of C6H12O6. All right, let's write our given in our grid. So we know we have 12 mole of H2O. Over 1. And we want to get to grams C6H12O6, right? So this time we're changing 2 things. We want to change the unit, but we also want to change the molecule. And remember, we can't change them both at once. So we're at mole H2O, right? And we want to get to grams C6H12O6. So let's go back and look at our equality list and see if we can figure out what to do. All right, let me put our equation here so we can kind of look over it. It'll make it a little easier. Okay, so we're starting here, right, with mole H2O. And we want to get to grams C6H12O6. So if the first thing in our grid is mole H2O, I would suggest we're going to use the mole ratio, going from mole known to mole unknown. That'll get us to mole C6H12O6, right, mole unknown, and then from our mole unknown, we can figure out the molar mass of the unknown, which will get us to the mass of the unknown. All right, so let's do that. So we have 1 mole of, see, our known is, or so 6 mole of H2O, and 1 mole of C6H12O6. So on the bottom is going to go our H2O because we want to cross that out. So we're going to have 6 mole H2O on the bottom. And the top is going to go 1 mole C6H12O6. Let's make sure our units cross out. So we're at mole H2O, and we're left at mole C6H12O6, right? So we've now changed from H2O, right here, right? We've changed from H2O, and we're now at our glucose. So we've changed molecules. Now we need to try to change from mole of C6H12O6 to mass C6H12O6, which, if you remember, we're going to use 1 mole of the unknown, C6H12O6, to the molar mass of the unknown in grams. And where do we get the molar mass? You add up the mass off the periodic table. So let's do that. All right, so we want 1 mole of C6H12O6, which we're going to put on the bottom because we have that on the top to cancel out. So that part's pretty easy. 1 mole C6H12O6 on the bottom. And now we need to figure out the molar mass of C6H12O6. So as a quick review, if you look at the periodic table, we have C is 12.01 grams, H is 1.008 grams, and O is 16.00 grams, right? And there are 6 of these, and there are 12 of these, and there are 6 of these. And when you add all that stuff up, my calculator, I got 180.156 grams of C6H12O6. And then we need to look at sig figs here. And because we're adding, we're looking at not sig figs, but digits after the decimal, the least number. So we have 2 there, 3 here, 2 here. So we're going to end up with 2 digits after the decimal. So we're going to have 180.16 grams of C6H12O6, which we will put up here. 180.156 grams C6H12, oh goodness, O6. All right, let me erase this stuff on the bottom so we have a little bit more room to work. All right, so now let's multiply. Oh, no, let's not do that yet. Something more important. Let's check. We're crossing out mole C6H12O6. And then I'm going to double check. I am at grams C6H12O6, which is what I was looking for. So now all we should have left to do is multiply and divide, and as long as we don't make a mistake in our calculator, we should be good to go. All right, so multiplying across the top, we have 12 times 1 times 180.16 grams C6H12O6. And that gave me 2161.92 grams C6H12O6. Multiplying across the bottom, we have 1 times 6 times 1, giving us 6. So when we divide, I got 360.6 0.32 grams C6H12O6. And our last step is to check sig figs. And this is a complete disaster here. Hopefully you guys will be able to see this. We have to check our given, right? We do not worry about the mole ratios, but our molar mass was also calculated. Our 180 point, not really sure why we're at 156 there. That should have been, sorry about that, 116. Okay, so we have 3 sig figs here. And in our molar mass, we have 5 sig figs. So we'll be using our 3 sig figs, which is this. We can't just write 360. Oh, since we're dropping after the decimal, we can just drop those. We can't just write 360 because 360 is only 2 sig figs. So you can write 360 with a decimal. Or you could write 3.6 times 10 to the second. Either way would be fine. Both of those give you 2 sig figs. No. We want 3 sig figs. There you go. And then, of course, grams C6H12O6. All right, I know this lecture is getting quite long, but I'd really like to try one more problem with you where we can incorporate mole conversions with our stoichiometry. All right, so our example is, how many molecules of H2O would be formed if you're starting with 245 grams of C6H12O6. So again, let's write our math problem. I'm going to need a lot of room on this page. So let's see. If we start with 245.6 grams of C6H12O6, how many molecules of H2O is that? And let me move this out of our way here. All right, so I moved the question down on the bottom. Hopefully I'll have enough room to do this problem. So we always start with writing our known, which is 245.6 grams of C6H12O6 over 1. Okay, so again, we're going from grams of one molecule to molecules of another type of molecules. So let's go back to our list of conversions and see if we can come up with a plan. All right, let's put our question here so we can see it. All right, so we're starting with grams of C6H12O6, right? So that's our known, and we're at mass, which is here, grams, right? So we're going to start by using this guy. 1 mole of our known equals molar mass of our known. That will bring us to grams of our known. Moles of our known. Now we can switch to our unknown. So we can use mole-mole ratio, mole of known to mole of unknown. And that's not going to get us to molecules, but let's stop there for a minute, and then we'll move forward. We'll finish up to here, and then we'll figure out what we should do next. All right, so first is 1 mole of our known, C6H12O6, equals the molar mass of our known. And I'll cheat a little bit. We figured that out on this particular problem here. The molar mass was 180.16. So Because we have grams here, we need to have grams of C6H12O6 down at the bottom. So that was 180.16 grams of C6H12O6. So on the top is going to go 1 mole of C6H12O6. All right, let's cross out our units. So we were at grams C6H12O6. Those cross out. We're now at mole C6H12O6. And we want to now get to mole of H2O. So we're going to use the mole ratio from the balanced equation. And we're interested in this one and H2O, this one, right? So on the bottom, we're going to put 1 mole C6H12O6. And we put that one on the bottom because we have C6H12O6 on the top. And on the top is going to go 6 mole of water. Okay, let's cross out our units. Mole C6H12O6, 2 mole C6H12O6. We are now at moles of H2O. The problem is we wanted number of molecules of H2O. So back to our conversion factors we go, and it's not listed, but let's remember that we learned that 1 mole of something, 1 mole of anything, can equal 6.022 times 10 to the 23rd molecules of something, and I'm going to abbreviate that as molic. Okay, so that will get us from moles of water to molecules of water. So on the bottom, I will put 1 mole H2O. And on the top, we'll have 6.022 times 10 to the 23rd molic H2O. Okay, so again, let's cross out our units. We went from mole of water, and we're left at molecules of H2O. So we went from mass of glucose to mole of glucose, and from mole of glucose to mole of water, and then from mole of water to molecules of water, which is what we wanted. So now we need to multiply across the top, and when I put that in my calculator, I got 8.87409192 times 10 to the 26th molecules of H2O. And when I multiply across the bottom, I got 180.16. So from here we divide, and I got, when I divided, let's see, 4.925632, etc., times 10 to the 24th molecules H2O. And the last step is sig figs. So using for our sig figs is our given, which is 4. We don't worry about the moles. We do need to worry about the molar mass because we calculated that, and that's 5. So those are the two things we're going to look for our sig figs. So it looks like 4. So we're going to keep those there. So final answer, whoa, what am I doing? Let's try that again. We're going to keep those 4 there. And of course, we need to keep the move your molecule. That's not part of sig figs. So our final answer will be 4.926 times 10 to the 24th molecules of H2O. All right, folks. So for stoichiometry problems, you need to be neat and careful. Write your units, write your molecules, make a plan. And remember, you can only change units or molecules at a time, not both. Just take it step by step and all will be good. All right, that's it for today. Have a good one.